I'm Bill Snodgrass, and in this episode of The World Around Us, we're looking at heat exchange problems. Where, and if you're not completely familiar with the concepts, there's a link to a concept page. This is kind of the math solution video, but there's a link to the sort of a concept page where you can go and read about the concepts of heat and thermal energy, which is, we're going to use them interchangeably, heat and thermal energy. And they're going to be represented by the variable Q of all things. And so the problem says something like this, the problem that we're trying to solve. Now there's like, we're going to do like the both sides of the equation, but sometimes you'll get a problem that says how much heat was given off, and sometimes you'll get a problem that says if this much heat was given off, then what is one of these values, mass, specific heat, or change in temperature, or something like that. So this problem is going to require us to do both of those steps. We're going to talk about that as we go. So the question says something to the effect of a 1 kilogram sample of lead is having an initial temperature of 300 degrees, is placed into a container of water with an initial temperature of 68 degrees. If the final temperature is 75, what was the mass of the water? Given that the specific heat for lead is 129 joules per kilogram degree Celsius, and the specific heat for water is 4,128. All right, so we got two problems going on. So the way that I introduce and teach problem solving is, first of all, write down what's given and what you're looking for, find some relevant equations, plug in the numbers, and solve. So write down what's given and what we're looking for. So in this problem, we're going to have something that is giving up energy and something that is gaining energy, and I'm just going to collect those over here at the top. So I have my loser. This guy is losing energy. This is the lead. The lead is losing energy. The mass of the lead is 1 kilogram. The specific heat of the lead is 129. We're going to need delta T, but we're given Ti and Tf. Delta T, we're going to have to calculate that. Ti is 300 and T sub F is 75. I ran out of room, as I do, ran out of room. That's an equal sign, not a Z. On the gain side, that's the water. We're supposed to find the mass. The specific heat is 4,128. Delta T, we'll have to find that. Ti is 68. And T sub F is 75. Now here's the first thing to note. On these heat exchange problems, the final temperature is the same on both problems. The final temperature is always the same because they mixed and they got to a final temperature. We need our relevant equations, and there's two relevant equations. That is, the one is heat lost is equal to heat gained. Heat loss is equal to heat gain. So put two things together. The lead has extra energy. The water has deficit in energy. You put them together. The lead gives that energy to the water. So the amount that is lost is equal to the amount that is gained. Heat loss is equal to heat gain. The second is that energy, Q, is equal to the mass of the substance, the specific heat of the substance, and delta T. Delta T being the change in temperature. How do you find delta T? We need it for both these equations. Delta T. Delta T is initial temperature minus final temperature. And you can be complicated about it and worry about the positives and minuses. But when we're saying the amount of heat lost is equal to the amount of heat gained, we're dealing with the minus sign there. So all we do is really basically we're taking the absolute value. So I have a calculator if I should need it. 300 minus 75 is 225. That's delta T on the lead side. And delta T on the water side is 75 minus 68, which is 7. All right, there's our information. There is our relevant equations. Let's get going. Since heat lost is equal to heat gained, we're going to start with the heat loss side because we have all of the numbers on this side and we are missing one of the numbers on this side. Some physics problems, chemistry problems will give you, they'll say how much heat is involved in this process, and that's what this first part is. So if you have a question and all it asks you is how much heat was given off, all you have to do is step one. Step one, heat lost. Q equals MC delta T. Q, that's what I'm looking for. M is 1 times specific heat is 129 times delta T is 225. And just in case you're not seeing these numbers, so I've got mass here, and that's mass, and I've got specific heat here, got these out of the story, whatever the story was, and then I have delta T, which I calculated. So I take those numbers and I plug them in. And if all you have to do is find the energy, then you are ready to multiply those numbers. 1 times 129 is 129, and then times 225 is Q equals 29,025. And I have notes. I didn't do that in my head. I could have used the calculator, but I have notes. If your question is how much heat was given off or how much heat was absorbed, that's all you have to do. Plug in the numbers, solve. If you have to find how much one of the other values was, like mass, specific heat, or delta T, now you got to do the heat gain side. The heat gain side, the same equation, Q equals MC delta T. Q is Q. I'm looking for the mass. C is C. And delta T is delta T. This is from the heat gain side here. This is the information that's going down. Q, heat loss, is equal to heat gain. And so therefore, they plug in. 29,025 equals, I'm looking for M, times C is 7. And C is not 7. Delta T is 7. Because multiplication has that property, doesn't matter what order you do it in, I'm okay, I'm still fine. Multiply these two numbers, and then I'm going to divide this number by those two numbers. So I've got, move up the paper a little bit, 29,025 divided by 28,896 equals M. And when you divide that, you get 1.0045. So the mass of the water was 1.0045. Now, if you have a question that says, what was the specific heat if this much? And so this is like one of the types of questions where you're looking for one of the pieces when heat is given. If you have a question that says, find the amount of heat that's given off, supposing that everything else is given, this is it. And then if you have a question that says what this one said, a lead sample is put in with the water and the final temperature and they mix, and what's one of the pieces of one of the sides, then you have to do both steps. There's 5 steps to this. One is to find the heat here, you have to subtract to get delta T, and then you multiply. Then you copy Q down, let's say that's the third step, and you subtract to find delta T, And then you multiply and divide, and that's your fifth step, multiplying and dividing in order to find whatever is missing. And the math is the same whether you're looking for M, C, or delta T. In this case, we were looking for M given the other quantities. So the heat exchange problems are not that complicated mathematically. There is an organizational process to it. And the typed version probably illustrates that better than my handwritten, even though I had fancy highlighters. That's it for this episode. Thank you for watching. Please click the like button, subscribe to the channel, sign up for notifications, leave me a comment, question, or suggestion. That is all for this episode. We will see you in the next one. See, I know the video is the right length when the coffee has cooled down enough to drink it before I'm done. Hi, I'm Bill Snodgrass, and in this episode of The World Around Us, I'm going to start over.